How are you doing? So maybe you don't fancy picking somebody's brain, or maybe spending the whole day in a lab with bottles with other people's urine. My name is Roland Lindh, and I'm here to offer you an alternative. I'm going to talk about theoretical and computational chemistry, an ultimate way to understand and simulate chemical processes. So I always ask myself, why do we do chemistry? And the reason is we would like to understand the chemical reactivity and use our fantasy to design materials that have the properties we would like them to have. And the lectures you've been listening to here just reflects that need. I have some examples here. So we would like to design drugs to maybe inhibit an enzyme. We would like to design batteries for our mobile phones on computers that performs optimal. Or we would like to design solar cells. All these have been mentioned by the people before me. Or maybe we would like to design smart materials like Teflon or Kevlar molecules. Or we would like to design some smart alloy that has some property we would like to have. How do we solve this? Well, all of us are chemists that are present here today. And we come up with a hypothesis. This is the way it works. This is the way it should work. And we make a hypothesis, and then the next thing is we try to verify that. And what's usually been done for hundreds and thousands of years, is you go out in the laboratory. You design an experiment to demonstrate that your hypothesis is the way it works. But since a few years back, there is an alternative. You become a computational chemist. You design a simulation to prove your point. Now, how does this work? Well, let me try to explain this. Anybody heard of a Turing test? Right? You have a person sitting here in a room, and he's in contact with something. It could either be a computer or a person. And the game is now that with the smart questions, figure out whether it's a computer or a human being. Quite recently, there was a computer that could fool people to believe it was a 12-year-old person they were talking to. That's how far computers have come today. Could we have a Turing test for chemistry? Well, I'm offering you an alternative here. Here are two spectra. One is experimental, and one is derived from a simulation. Which one of these would you pay money for? Well, it really doesn't matter. You would ask the question, which one can I get the most efficient, the cheapest? That's the relevant question. With theoretical chemistry, we can simulate chemistry as it is with a one-to-one mapping. Now, let me try to briefly explain what computational chemistry is. And I'm going to sidetrack and look at CAD-CAM technology, which is everywhere in society today. The way we design cars, airplanes, train, or whatever, we simulate these entities on computers to make sure they have the properties we would like them to have. And if they don't have that, we don't produce them. We only produce things that has potential to do the things for us. I've listed a number of things here you can check with simulations today. There's a difference, though, with computational chemistry. Here we have entities that are large, and we can simulate those with Newtonian mechanics. Electrons are elementary particles, and we have to use quantum mechanics and quantum chemistry. Otherwise, it's the same story. We can, with theoretical chemistry and computational chemistry, simulate any known compound or any compound that will be known and all those that will not be known. any composition you put together, we can simulate and test their properties. A few words about the methods we're using. There's a small equation here called the Schrödinger equation. There's a small picture, that's Irving Schrödinger. There's a larger picture here, or equation. This is Paul Dirac. These are the cornerstones in the theory we need to describe how a molecule behaves. And then, of course, we need the computers. So we have quantum chemistry. We take these equations, we make approximations, we put them on the computers, and we call these methods, when we do the calculations, for ab initio methods. Why ab initio? It means from the beginning. The only thing we assume, apart from the equation, is that the charge of an electron is -1. That's the only assumption, and then we try to do some smart approximations. I'm going to show you some examples of what our simulation techniques and other simulation techniques can demonstrate. So here we have a movie. Actually turns out to be a movie with one of the molecules Helena showed us. Let's see now. Here we go. So this is transfer RNA ribosome, and we're going to see a simulation here to demonstrate how this molecule operates using the messenger RNA down here and decode it to pick up amino acids and put together a protein. Here it's picked up an amino acid, and the arm now swings in to the place where the synthesis is going to take place. I'm apologizing for the poor quality here, but that's how it looks like. You see the green molecule here? It's going to swing inside the ribosome and dock up and put it in the right place for the synthesis of the protein to take place. Showing this now from various different perspectives, so I think we go over to something else here. This is a molecule we've been doing calculations on in my group. I'm very interested in the interaction between matter and light, in particular the one that makes it possible for you guys to see me here right now. In your retina, there is a molecule called Rhodopsin that looks like this. It's a conjugated system, and when it's hit by light, it goes through an isomeric reaction, and it makes a twist. And this twist eventually gets translated to an electric signal, which propagates back here, and you will see me. Now, the important thing is this double bond here. This is results from quantum chemical simulations. The red here reflects the pi system, the conjugated system. Now look very careful here, because that's where the twist takes place. Oh, sorry. And you see these two hydrogens switched over like this. Understanding this process will allow us to, first of all, understand why different molecules are sensitive to different wavelengths, but also it allows us from the molecular orbital level to understand the process and start to modify it to our preference. So a molecular orbital understanding of all these chemical events that take place puts ourselves in a situation where we can start to modify things according to our preferences. We have other research on our group. Hydrogen storage. I think some of the other people have been talking about the fuel of the future. We need to store the thing. This is a compound we have designed. This is a molecule that doesn't exist today. It exists here on my computer, and we are trying to test this to see what do we need to do with this molecule such that it becomes optimal for hydrogen storage. Here's another system. how can we do small systems that have functionalities? And one thing some chemists have been dreaming about is how can we do small molecular vehicles? And the first thing to try to design is a motor. Here's a motor that's been designed by a colleague of mine, Leticia Gonzalez, down in Vienna, where she's using this reaction here. You shine light for this step, you add some energy here, etc. And this molecule will start to move around. This is also, again, from a quantum chemical simulation. And finally, we are looking at chemical reactions and trying to understand their thermodynamics. How do the transition state look like, etc. And you can take any reaction from any of the fields that my colleagues represent, and we can do the simulations. Here is a system that goes through, this is an allyl Coop rearrangement. We're going to build a bond in between here. We're going to go from the product to the reactant and back to the product. Let's see, here we go. Bond forms, and then we go back. And we can freeze these very fast reactions and look at them and try to understand what happens if I add a substituent here, or what happens if I do this, or I change a group over here. Theoretical chemistry has a lot of potentials. Theoretical chemistry is not only doing these simulations, but actually also to design the software and how to use the computers to do these software. So that's what we call method developments. So I'm at the end here. I would say that theoretical chemistry techniques have an enormous potential, and with the development of smarter and better computers, this is going to have an enormous impact on how we do theoretical chemistry. Theoretical chemistry allows us to explain phenomena down on a molecular orbital level. It allows us to look at how nature has done it and try to learn from it and see how did nature put together the molecular orbital puzzle. It allows us to design new materials without having to figure out initially how to synthesize it. But once we have selected how to synthesize it, we can again use theoretical chemistry to design the synthesis. So I would say this is a technique that is only limited by your imagination. So welcome to the future and your new career. Thank you very much.